Hello everyone, welcome. This video is to teach you how to use backbone matching. To access backbone matching, we will need to go to the Burgess group website, burgessresearch.org. We will enter here and you can see multiple panels at the top list. And we will go to the software panel, which can show you multiple softwares developed by Burgess group. And you can find backbone matching here. There is a part code where you can click it. It will lead you to the GitHub repository of the backbone matching. This GitHub repository includes several folders as well as a README introduction. So I will lead you through this README introduction. First of all, this script for backbone matching are designed for Linux systems, so it is recommended that you use them on Linux machine. The recommended language is Python, and it is recommended to download these packages, PyMo, Pandas, and NumPy before running the script. Before using the script, we need to prepare 4 folders in the same directory. They are loop targets, conformer for matching, align result, and mimic result. The loop target is the folder where we store the loop structural files. Those structural files should be in PDB format and should be saved in this folder before running any script. The second folder is conformer for matching. This folder is used to save the conformers of 602 cyclo-organopeptides. So these conformers can be obtained from the dataset folder in this GitHub repository. So we will click dataset and go to the conformer folder. And here there is a link for you to download these conformers. You will only need to copy and paste it here. It will lead to a Google Drive, and you can download these folders one by one to insert them into the conformer for matching directory. So here I give you a basic impression of what this folder looks like. We'll have the conformer for matching. Inside it are 7 folders which represent the length of cyclo-organopeptides that can include 4 amino acids to 10 amino acids. Inside this length is 86 different adenine sequences to form cyclo-organopeptides, and inside them is the specific conformer of cyclo-organopeptides with that specific length and that particular organic fragment. So this conformer file should be prepared under this sequence. The third and fourth folder, align result and mimic result, should be empty folder at the beginning, and they are used to store the result of the backbone matching. Align result is to store the IMSD value, while the mimic result is to store the best overlaid conformer. After you prepare these 4 folders, you will need to download the 2 alignment scripts. The first script is precise alignment. The second script is auto slicing alignment. This script can be downloaded under the script folder here. You go to script, and then you go to, for the precise alignment, you will go to the precise alignment folder. For the auto slicing alignment, you will go to this folder. So you only need to click it, find the file, and download it. Make sure that this Python file are stored in the same directory as these 4 folders. Next, I will introduce how to use this alignment Python script. For the precise alignment, the input is Python precise alignment dot the loop name, number of hits to store, length of input loop. So for example, if I want to find hits for uPA loop which has 8 amino acids, so the input should be Python precise alignment dot py uPA 50 hits to store and 8 amino acids in the loop. The output is IMSD value in the folder align result, and the overlays of those hits will be output as a PyMo file in the same folder as these different directories. Auto slicing alignment is easier to use. To run it, you will only need Python space auto slicing alignment.py space loop name space number of hits to store. So again, for uPA, when we need to run the auto slicing alignment, the example input is Python auto slicing alignment.py uPA and 50. Here we don't need to constrain the length of the loop because auto-slicing will cut it into shorter lengths to find hit comprehensively for those smaller fragments. Again, the output for the IMSD value will be stored in the align result folder, and you will also have a PyMol file in the general folder for you to visualize the overlays. Next, we will take a look at the output of the script. The output of the precise alignment for uPA fragment is given in the folder of illustrative output, which is named as uPA 2330 precise scan, while the output for the auto-slicing alignment for that uPA fragment is stored as 3bt1 uPA scan.pac. This can be found in the illustrative output folder, and you can download them from here. I can give you a lead of what these files look like. I have already downloaded them here, and for the precise alignment, we get a result like this. We can open it in PyMol. We will zoom so we can find the structure. So the precise alignment only focuses on one fragment of the loop, and that loop includes 8 amino acids. And once you open it, you can see a list of cyclo-organopeptides which overlays well, and the earlier hit represents a better overlay. So let's look at them. So if we deselect all the cyclo-organopeptides, we will have the loop, and then our top hit using this scaffold, the second best hit using this scaffold, and the third best hit using this scaffold. The decision of which linker to use is very subjective. It depends on the price of the organic fragment, the easiness of the cyclization, and as well as the steric hindrance between the linker with the receptor surface. So this is a sole decision by the user. Next, let's take a look at the output from the auto-slicing alignment. So unlike precise alignment, auto-slicing alignment has overlay result for loops with different fragments, and you can check them one by one, but here I will only use the first one as an example. So the first one is to find best overlay result for the loop fragment 25 to 29, and we use 4 alanine cyclo-organopeptides to do this. This is the loop fragment, and we can find the best overlay hit like this, like this, like this. So again, the choice of linkers is solely determined by the user, considering different properties and requirements. The user is also interested in the overlay IMSD. They can go to the online result folder to find it. So here we go to the online result folder, and we want to visualize the overlay IMSD of the uPA fragment by precise alignment. So we'll go to this folder, and we can find a CSV file which includes the overlay IMSD. The first value is the overlay IMSD. The second value is the top hit, and the last is the loop fragment. So user can find the exact IMSD values for the overlay from the CSV file in the align result folder. So this is a comprehensive introduction to the backbone matching, and if you like it and use it in your research, please cite it with this citation. Thank you very much.